In this video, we will explain how to control for a constant angular velocity of a rigid pendulum arm attached to a motor, despite being subject to the force of gravity.
A DC motor can be modeled as a resistor, inductor, and voltage source in series. When taking measurements, we know that the current through the motor is proportional to the torque, and the voltage V EMF is proportional to the angular velocity or speed. We will use these values to measure the behavior of our motor once we begin to control it. We know that the impedance of the motor is the resistance of the resistor plus the product of the inductance and S. The intersection point of this Bode plot lies at 500 Hz, and all frequencies less than that have a constant value of R. Since our rotational frequency will always be well below 500 Hz, we can ignore the inductor in our motor.
To control the angular velocity, we first need a way to find this velocity. There is no direct way to measure VEMF since the voltage drop across the entire motor also includes that across RS. Thus, we have the source meter circuit, which takes in a current proportional to the electric torque of the motor and outputs a voltage proportional to the angular velocity. The source meter can be simplified, shown here. By correctly tuning the ratio of the effective resistors from the potentiometer, we can isolate the part of the motor's voltage drop that is proportional to angular velocity. Let's analyze how the system behaves. From Newton's second law of rotation, we know that the sum of torques is equal to the moment of inertia multiplied by the derivative of the angular velocity. In our case, the net torque is the electrical torque and a quantity proportional to the angular velocity. In this equation, I and B are parameters of the motor that we won't discuss here. If we take the Laplace transform, we are left with an equation containing both S and the angular velocity in the frequency domain, noted here by the larger omega. By rearranging this equation, we can find the transfer function h. By equating the denominator with 0 and solving for s, we can find there is one pole in the system. This value is negative, so we have a stable first-order system. We are ready to control the system. We will be using proportional control implemented by the amplifier circuit shown here. This controller takes in the velocity reading and amplifies any difference between the velocity and the set point voltage to create a new value for the electric torque. From our previous analysis, we can substitute in the transfer function of the source meter into the torque value, which we can then equate with the error that we just discussed multiplied by the proportional constant. After rearranging terms, we can see the transfer function of our controlled circuit. By plugging back in the transfer function of the source meter, we can solve for the new pole of the system. Our model assumes a first-order stable system, where increasing Kp increases stability.
As you heard a moment ago, the system for a controlled rotating pendulum is made up of a source meter and a controller, and any error in speed is adjusted for in the controller. There are a few parameters we can tune to change our rotating pendulum's behavior. We can adjust the V-set potentiometer in the controller circuit to vary the speed and direction of our pendulum's motion. We can also adjust the potentiometer in our source meter to change how much or how well we are correcting. To achieve constant speed, this potentiometer should be set such that the ratio of the resistors is equal to the ratio of our RM resistor from our circuit and the internal impedance of our motor. This ratio is what you're seeing in the constant speed demonstration here. We can also vary our proportional control constant Kp by changing our resistors to increase the gain in our controller amplifier. We know from our pole zero diagram that a higher Kp corresponds to a more stable system and more constant speed. Let's take a look at our pendulum with a few different gains. Here is a gain of 10. Here is a gain of 67. Here is a gain of 200. You can see from our demonstrations that the higher the gain, the more constant the angular velocity stays. Next, we decided to control for position.
To control for a constant position in our pendulum, we have to make some changes from the previous circuit, which you can see here. Between the source meter and the controller, we add an integrator circuit. Since the integral of speed is position, this allows us to control our pendulum for a constant position. Similar to the speed control circuit in the previous demo, we can adjust some parameters in the position control circuit that will let us change its behavior. The pendulum here approaches upright if I release it from facing downwards, but each time it gets to the correct position it overshoots. But if I adjust the source meter potentiometer to change the ratio A, then the pendulum stops those fast oscillations and approaches upright much more smoothly. It still initially overshoots the upright position, but eventually settles into place.